Alright, so as a problem-solving example, I would like to look at this orbital motion problem. So we're going to look at a circular orbit of a large moon around a small planet. Now, the moon's still smaller than the planet, obviously, otherwise they'd reverse designations. And we have a distance between them, it's d. But we want to look at the orbit of the moon, the orbital radius of the moon, not the distance between them. Those are different things. And so the orbital radius, if we were to think about it, would be, let's say we had a planet and a moon, right? They've got that distance d. They're orbiting around a common center, like that. And so we're going to think that r should be greater than d over 2, right? This orbital radius for the moon, little r there. So well, I've already drawn a picture, so we're halfway through our setting up thing. What do we know about this? So we want to always set up our problem. One part is to draw it. We always want to draw our thing. This is a little hard. There's no friction on this pad, for example, but we still want to draw that thing. Then we want to look at our givens. What do we know about this? We know that there's a planet, one object, and a moon. So we always want to have, we want to break up the things we know as to which objects we know them about, right? So we have a planet that has a mass m, and a moon that has a mass, I guess, little m. And then we'll have a distance, a separation between them, d. Then we want to find the orbital radius. We'll give that a name, little r. Call it little r. So we know big D is the distance between these two objects. The moon has a mass m and the planet has a mass capital M. So we just read the problem. First thing we do is we read the problem, we try to figure out what's in it and where everything goes. We do that before we figure out anything else. We're not trying to solve the problem when we initially we're not trying to solve the problem when we initially read the problem. We're just trying to categorize things. All right. What we're trying to do is trying to get you to look at details without having to try to put everything in context at the same time. So we're breaking up the context into little chunks like that. Okay, so now that we've got that, now we can look at the bigger picture stuff, right? What's going on here? Well, we've got the moon and the planet. They're both moving, so the moon is always changing the direction of motion. Since it's changing the direction of motion, it has an acceleration. That means we're going to have a concept of Newton's second law. And so that will be associated with our usual equation for Newton's second law. The sum of all of the forces on the object, the applied forces, the sum of those is equal to the mass times the acceleration. These things are equal, so they're the same thing. They're the net force. This is the net force, that's the net force. Same thing. I guess you should call this the net force, the sum of the forces. And ma is the reaction to them. Then we need a representation. A representation for all of our force problems is a free body diagram. Let's say this guy's going this way. So our direction of motion is t, and our perpendicular direction is r. And there's only one force. That's the force of gravitation, gravity, between these two guy is here. That's our universal gravitation, and I call that F, the force of gravity. It's the same force over here as it is over here. Because this guy's more massive, he goes in a smaller circle than this guy because he's less massive. All right, so that's setting up the second part of our problem. So now we've got a bunch of stuff we know. We know we want to find the orbital radius. We know we're going to use Newton's second law, and we know we've got to use this relationship given by the free body diagram between the applied forces, the forces on the box, and the net force, this MA floating in the middle of nowhere, right? So just as some practice, right, we've got our applied forces, and we've got our acceleration. They're equal to each other. Over here, our applied forces, we have one force, that's F. We've got another one over here, which is MA. And this is in the radial direction. If I wanted you to give me both the radial and the tangential directions, the net force in the tangential direction is 0. There are no components of any forces in the tangential direction up here. And the acceleration over here is 0. There's no component of the net force in that direction. So your applied forces have to be able to sum up to this thing, meaning that if one of them is 0 in one direction, it better be 0 for the other one. Okay, so we're probably going to use this in our plan somewhere. But it's not what we get right away because we need to find little r first. We always start with the thing we want to find. Always start with the thing you want to find. And in this case, since we're going around in a circle, we have a centripetal acceleration. So I'll use that. As our first concept. That is, the centripetal acceleration is equal to the speed, the linear speed of the moon squared over the orbital radius. So this radius here, not that distance, this radius here. We're looking for r. And we don't know either of these quantities. We don't know AC and we don't know V. Linear speed's not too hard though, because we know that this thing's going to go around in that circle, right? And that circle has a circumference of 2 pi r. And it's going to go around that in a period t. So we can use the definition of average velocity, which says that velocity is equal to delta x over delta t. Our delta x is that 2 pi r, our delta t is t. So we already found that r. We were looking for the v. R gets a check mark. V gets an arrow because we're looking for it, right? It means we no longer have that question mark. Every time we go to a new step, we're looking for one of the things with a question mark. And we have an arrow pointing at the thing we just looked at. So here we have r because it's in the find. That's how we start the problem. You always have a way to start the problem. You have to start with this guy. Then we go to average velocity because we're looking for the velocity. So, I mean, the definition is good and we can figure that out fairly readily with the 2 pi r. R, again, we already have, so that's a check mark. And V, we're looking for, it gets a line. And T, well, it's right here, right? It's given. And this problem is, actually this problem is better if I don't give you T because then you find a really interesting answer. This is not going to give us the interesting answer, but if you have that T, if you don't have that T, if you have to solve for it, it doubles the amount of work on the problem, but it gives you a really, really nice answer. But what we care about here are sort of the concepts. We don't want to get into those details today. All right, so we've gotten rid of this. There are no question marks in 2, so the only choice we have is to find something with the centripetal acceleration. Well, how do we do that? Well, let's look over here. What is this acceleration? This is the direction of motion. This is the radial direction. The acceleration in the radial direction is the centripetal acceleration. So that's our centripetal acceleration over here. So we can put a little AC here if we like instead. F equals MAC. So why don't we do this? F is equal to MAC. Now which M do we put in there? We've got a big M and a little m. We've got the mass of the planet and the mass of the moon. The moon here is what we're looking at. We want to see this thing go around. We want the radius this thing turns, so we want to use the mass little MAC. All right, so we were looking for AC. That's the question mark here. Little m, it's in this list, so there it goes. And F, we don't have an expression for, but this is Newton's second law. Okay, and fourth, we're going to have to find this. This is the force of gravity, so we'll use universal gravitation. So F equals GMM over d squared. All right. This is a constant, a universal constant, so it gets a circle. We can always assume the gravitational constant. M and M, we're giving them both up here, so they get little squares. And D, we're given here. And that gets an arrow at it. That crosses out that question mark. So there are no more question marks, which means we're done. We've got our plan. All right, this is universal gravitation. Next, we want to execute on our plan. We want to play with our plan so that we can get a number, or we can get the answer to this question. How can we do this? Well, one tactic that's usually good is to start substituting things into the Newton's laws, right? Newton's second law, into the force equation. So we substitute things into the force equation. That usually means we've got like this guy to pull in here and this guy to pull in here. They both go in, right? So we'll just substitute 1 and 4 into 3. Okay, so we can cross those off, 1 and 4 and 3. We get to cross them off. We need to use each one of these equations just at least once. If we don't, we know we're in trouble somewhere. So we have GMM over d squared. That's substituting 4 in for F. So we're getting rid of the F by putting this guy in. That's equal to this guy here. So we have M times AC, which is V squared over R. Okay, so we've got that part done. That's easy. Like we said before, a lot of this, call that A, a lot of this is just substitution, right? The big work is setting up these equations, which is all coming from our concepts. Right? These are our concepts. So we have to understand those concepts in order to make the plan. And then we come over to the execution, which is the math. Most of our work is going to be substitutions. It's not really horrible. Let's get rid of this M here, and we'll substitute 2, right, into A. So we have GM over D squared is equal to V squared, which is 4 pi squared over times a little r squared, but we've got a little r in the denominator, so it's r over the t squared. Okay, so that's reasonably good. We've got everything done. We've got 2 there, and we used A. Have to use all the previous steps. So now we'll just solve B for little r, which is not hard, that's little r there. So we take gmd squared over d squared. The 4 pi goes in the denominator, and the t squared comes up here. Okay, so that's good. That's an answer. Like I said, it would be more interesting if we substituted for t squared, and you can actually do that if you want to, because this guy here follows the same law. So you'll get a similar equation here, similar equation to this one for this guy here. And so, remembering that this is d minus r, and you switch out the masses, you can then substitute for the t squared, and you will end up with this distance being the distance to the center of mass. But this is all this particular problem asked for. It's a little bit easier than all of that work. Now we want to see if this is an okay equation. So how do we do that? Well, we take each one of these symbols in here, right? So we've got G, M, T, and D. And we want to decide if it's given, if it's in here, it's universal, or if it's excess. If it's excess, we've done something wrong. We want to only have stuff that's given or something we can assume. Okay. Let's see. First of all, is big G in here? Not in the orbital radius part. Let's see. MMDT? No. So we don't know about that one. M. Big M is right here. That one's okay. Little m we don't have. Big T we have, it's right there. And big D we have, it's right there. So M, T, and D are given. About big G? Is it universal? Is it something we can assume? Is it something we can look up? Yes. So it goes there. And then that means we've got all those. We're good. So that, at least as a check, that's good. If that was wrong, we'd know we were wrong. Doesn't mean we're right, but it means we're not so wrong. All right. We also want to look at the dimensions. All right. So let's see, what are the dimensions of this thing? Well, we want the dimensions of R. R would be measured in, let's say, kilometers, which are a unit of length. And then we want to find the units of that guy, which are kind of hard. First, we have to remember what the units of G are. Right, G has units of L squared over MT squared. L cubed, excuse me. L cubed over MT squared. The mass has units of mass. The time has units of time. The period has units of time. And D has units of L. So that's squared. This guy cancels that guy cancels that guy. Two of these cancel all those, so we've got L. Okay, so they match. This guy and this guy match. We're done. So that's what we found here. So again, this isn't my most exciting way to do this. Getting rid of this would improve the look of the final answer and give you something interesting and physically meaningful. But this also gives you an example about how to work through one of these problems, which is the point of this video. It's not really to get you into some sort of essential truth. What we're doing, the main point of the class, is to solve the problems. This is the big part here. And again, remember that is, we're using concepts to solve the problem. What things are active here? What things are actually going on? We have to be able to think about that. We want to break it up into little chunks, one chunk at a time, right? So that's why we're looking at these question marks and these arrows, right? We need to figure out R first. It goes to an arrow. Now we've got these two guys. We're just worried about centripetal acceleration and velocity. We're not worried about anything else. So we'll take this guy and we'll get rid of him. Now we need centripetal acceleration. We get rid of him. We're stuck with the force here, so we'll find his value there. So by substituting our givens as much as possible into these equations, what we're able to do is limit how much of the problem we have to keep in our head at any given time. Right? We're not going to try to solve everything at once. We're just trying to solve one thing at a time. Don't want to say too slowly because we have to do this on a quiz, but just one thing at a time. Figure it out. That's all we need to do. All right. Bye now.